Uh, I don't need to say anything about this anymore. You guys know that you have 2 weeks to put something together. So next week, we'll probably hold office hours rather than have lectures. So you guys that would be a good time to work on your project if you guys want to meet during class time, and that'd be a good time to have your work session, just because the instructors will be here, and so if you guys have any questions, we can answer those. Today, we're kind of talking about a new topic. So for most of the semester, we talked about supervised learning, where we have labels for our data, or we have output values, our Y values that we can either regress on or classify. We did do one lecture on unsupervised learning, so maybe if you can think back to k-means, when we did k-means clustering, that was an unsupervised learning algorithm. And today we're going to talk way more about unsupervised learning and a lot of cool things you can do with it. And we'll focus today on one main algorithm called principal component analysis. Has anyone heard of PCA before? Cool. I see a lot of hands. Well, today we'll talk about it quite a bit, and we'll show you a bunch of applications. And then we'll talk a little bit about more deeper topics. Before I start, are there any questions? Cool. So this is our agenda for today. First, I'll just remind you all what unsupervised learning entails, a little bit of background information, and then we'll talk a great deal about principal component analysis, also called PCA. I probably won't say principal component analysis any more times after this. I'll just say PCA. And then I'll talk a little bit about nonlinear dimensionality reduction. So principal component analysis is a type of linear dimensionality reduction. It turns out a lot of data sets are better reduced nonlinearly. So we'll mention that a little bit and kind of open your eyes to that world. And then James will talk to you about a really cool application about zebrafish brains. Very, very cool application there. And then the last thing we'll talk about is eigenfaces, and we'll just do a little demo on eigenfaces. So I don't want to ruin the surprise yet. If you don't know what an eigenface is, they're pretty cool. But think facial recognition. So any kind of facial recognition software, they might use eigenfaces. So what is unsupervised learning? Again, we don't have classes, we don't have labels, so it's quote-unquote learning without a teacher. I don't know what class I belong to, but I know I belong to some class, I just don't know which one. So again, I observe n observations with p features, our general setup when we observe data. So again, I observe n observations with p features each, and I denote my sample point x, and often, a lot of the times in unsupervised learning, we see that the dimension of x, denoted by p, is much higher than in supervised learning. So a big kind of goal in unsupervised learning is dimensionality reduction. So I say here that there are many methods to identify low-dimensional manifolds within the x space, the data space, that represent the high-dimensional data. So I have this very high-dimensional data, and I'd like to be able to approximate it in a much lower dimensional space. Again, because I don't have labels, and when I'm trying to classify things into groups, when I'm trying to cluster things or do some kind of grouping, I don't know how well I'm doing because I don't have labels. So a problem with unsupervised learning is that there's no measure of success. I don't have a loss function or a cost function that we're used to seeing with supervised learning. So there's two popular techniques in unsupervised learning, cluster analysis and dimensionality reduction. So you guys have all seen cluster analysis when we talked about k-means. I'll briefly talk about a couple other clustering algorithms, and then the bulk of today will focus on dimensionality reduction. So cluster analysis. You guys have seen this before. It's where we group a collection of objects into clusters, such that objects within each cluster are more similar to other objects in that cluster than to other clusters. And these are some popular clustering algorithms. You guys have seen k-means before. K-medioids is often a very popular one because it's less sensitive to outliers. Hierarchical clustering is what we see here. So this example here is we have states. We have crime data for states, and we don't have labels for different states for. We don't have labels for that, so we're trying to group states with similar crime statistics. So you see that all the black states have very similar crime statistics, the red ones are similar, and so on. So that's an example of hierarchical clustering. And I don't have time to tell you about all these clustering algorithms. There's a ton of them. I just wanted to open your eyes to existence of them. So if you want to do some more clustering on your own time. And again, we talked about most of these ideas when we learned about k-means. So here's an example of pretty cool example of clustering, where we have our data is different information resources. So imagine I'm on Google and I'm looking for different resources for my project or something like that. And I'd like to be able to group the sources of information into different categories. So maybe at a high level, I can group them into engineering, social sciences, and sciences. And I can go deeper and say that within engineering, there's a computer science cluster. There's a mathematics cluster, which is also related to science. In social sciences, there's an information and library sciences cluster. And then I can go further and further into more detail. So that's just kind of a pictorial example of clustering and how that we might use clustering. So, like I said before, a big problem in unsupervised learning is that our dimension of our data is very large. So, again, we have very many features that are sometimes redundant or counterproductive, as we'll see later. Sometimes the extra features are just hindering our accuracy. We could do better if we didn't have all the features. And also, as we increase the number of features, it costs more to compute models and stuff. It costs a lot more to train and test these models when I have a lot more features in my data. So a big problem with this is computational efficiency. So again, our goal here is to be able to separate noise from the features that capture the phenomenon being studied. So how do we, when we have this large dimensional data, how do I extract the relevant stuff from the noisy stuff? And how can I only use the relevant stuff? So the solution, dimensionality reduction. So we want to reduce the number of variables under consideration. There's kind of two subfields here. We talked about feature selection back when we talked about linear regression. We can do forward selection, backward selection, kind of try and just remove the features and compute our models again and see what happens. Our more interesting approach to dimensionality reduction is to do feature extraction, which is what we'll talk about today. So this is where we're transforming a high dimensional space into a low dimensional space. So there's many kinds of transformations, but there's two groups that I like to think about them in. We have linear transformations, which include factor analysis and dependent component analysis, and in boldface, principal component analysis, kind of one of the most important ones. And then there's also nonlinear transformations, and this is where we see autoencoders, principal curves and manifolds, etc. But for the most part, PCA is pretty widely used. So what is PCA? So I like to think of it as a tool for exploratory data analysis and for making predictive models, kind of the two ways I usually use it. And formally, I'll just read this off. It's a statistical procedure that uses an orthogonal transformation to convert a set of observations of possible correlated variables into a set of values of linearly uncorrelated variables called principal components. So, as you see in this picture, we have x is our data points, x and y, or these red x's are our data points, x and y are our original coordinates, and we like to do an orthogonal transformation to convert our data into this principal component space. So these are the PCA1, these PCA2 axes are just the new coordinates in our principal component space. That we think is a better way to look at this data. So this is one way you can use principal component analysis. So let's say I have data in 3D. It looks like that. I know I have 4 classes in this case, red, blue, purple, and green. And if I do a PCA and reduce it to 2 dimensions, then I clearly see these clusters, and these clusters become very apparent. So in the first picture, maybe it's apparent, maybe it's not apparent, but once I do a PCA, the clusters are very apparent. So now I know, with a very high degree of certainty, that the purple points all belong in a cluster together, and the green points all belong together, etc. So this is what I meant by exploratory data analysis. It's a good way to visualize classes when you don't know what the classes should be. So these are just some applications. There's a very long list. I could fill 20 slides with applications, but at a reasonable level, here's some that I thought were important. So exploratory data analysis, which is kind of where we have this very high dimensional data, and we'd like to be able to look at it. I mean, I don't know about you, but I can't visualize anything greater than 3 space. I have a hard time visualizing 4D, let alone 1,000 dimensions. So PCA is a good way to reduce very high dimensional data into maybe 2D or 3D, so I can look at the data at a much more visible level, an interpretable level. Yeah, Shannon.
How do you know you're not losing valuable information?
You might be. So we'll talk about that.
Okay.
So another application of PCA is for data pre-processing. So this is what I was saying before, where maybe I have so many features and a lot of them are just noisy or redundant. And so maybe I'd like to reduce the dimensionality and only retain the important things and extract them from the noisy things. And so this is important. The second bullet point here, where I say PCA minimizes the information loss incurred by reducing the number of variables. So there's many different ways to reduce the number of variables. It turns out that running a PCA is the way to do that minimizes the information loss. And that's a very involved proof to show that. I don't have time to go over that, but just take my word for it that PCA minimizes the information loss when you're reducing dimension. If you know anything about the singular value decomposition, I don't expect you to, but if you've heard of an SVD before, the PCA and SVD are very intimately related. And we know that the SVD is the best rank K approximation to a large dimensional matrix. So we can talk more about that after class if you want. But some popular examples of PCA are in neuroscience, finance, when maybe I have a very large portfolio and I have all these different stocks I'm looking to trade, and I really only care about 3 or 4 important ones that are affecting the value of my portfolio at a high level. Computer graphics, meteorology, oceanography, gene expression, the list goes on and on. One particular example that I'm well versed at is gene expression or anything with genomics. So usually in genomics data, I have maybe a small number of patients in my study. I have maybe 1,000 patients. But for each patient, I have very high dimensional measurements. So if I look at a patient's bacteria level or something, they might have 1 million different kinds of bacteria in some cotton swab or something. So I have 1,000 patients and 1 million bacteria, but I'm pretty certain that all those million bacteria are not important. So PCA is useful here because it can allow me to really isolate the important things in my bacteria sample to see what's really affecting the presence of a disease or not. Again, it's used everywhere. These are just a blurb of papers that James and I found where PCA can be used. In literally every single possible field you can think of, PCA is used. In horticulture research, in computer network attacks, in cancer detection, in public parks, aesthetic values, everything, material science, hydro treating, everything. Yeah?
So why is it like noted as like the main thing? Like it seems like it's more for some pre-processing stuff.
It's a very popular technique used in dimensionality reduction. And also it's, like we just talked about before, it's the best low dimensional approximation. And so it's a very useful way to visualize high dimensional data in a 2 or 3D scale to kind of just interpret what's going on.
Okay, so it's a way of like simplifying the problem.
Yes. So for those of you who don't know, knowing what an eigenvector and an eigenvalue is very important to understanding PCA. So if you don't know what an eigenvector or an eigenvalue is, James will remind you.
Oh, okay. Yeah, so eigenvectors sort of geometrically, if you think of the eigenvectors of a matrix A, where A is a transformation matrix, like any matrix is a transformation, they're one and the same thing, a linear transformation. So you can think of this matrix that does this sort of transformation like this skewing here, and then the eigenvectors of this transformation are the vectors that don't change direction in this transformation. So you can see here this blue vector and this pink vector. In both the original form and after the transformation, they're still pointing in the same direction, but they've just been scaled by a factor of lambda, which is called the eigenvalue of the or eigenvalues of the transformation. So each eigenvector has a corresponding eigenvalue. Any questions about that? Shannon?
Do you guys consider imaginary eigenvectors?
What do you mean, do we consider?
Or like, sometimes the matrix have imaginary eigenvectors, right?
Yes.
Do you still perform calculations on those imaginary?
So the question is, what happens if our principal component is complex valued?
Yeah.
So the eigenvalue has a complex value?
Or the eigenvector? Oh yeah, they can. Yeah. So yeah, the eigenvectors are always real.
But the eigenvalue
Can be complex.
Can it?
Eigenvalues can be complex all the time.
But then it's no longer an eigenvalue.
No, it's still.
Either way, when we do PCA, we're not concerned with the eigenvalue itself. We're more concerned with V, the eigenvector, also called a principal component.
Any other questions before we move on?
And if you haven't seen eigenvectors, eigenvalues before, I mean, be very hard to teach you what they are right now in 5 minutes. So hopefully this is a refresher for most of you. So let's get into the meat of the algorithm. How does it work? So again, the principal components of a set of data in p-dimensional space provide a sequence of the best linear approximations to that data of rank. So I'm using the letter K here to represent my lower dimensional subspace that I'm projecting on. And I'm going to assume K is much, much smaller than P, the original dimension. So look, this is the algorithm right there. Very simple. I have data matrix X. So maybe X looks like this, where these are the sample points. And these are the features. And the first step is to center the matrix X. So I take all the features and divide or subtract the mean of each feature from the column of features. I then can optionally normalize X, which means I do some kind of scaling to convert all the data to the same scale. So if I have measurement data that's on different units, I'd probably want to normalize. But if all my data is on the same scale of measurements, then I probably would not need to normalize. After I normalize optionally, I want to compute the unit eigenvectors values of X transpose X. So X transpose X is, X transpose X, and I compute the eigenvectors of that using some kind of built-in eigenvector solver in Python or your favorite programming language. And then, that's a typo there. I say choose Q. I meant to say choose K based on the eigenvalue size. So when I run this PCA, I get a list of eigenvalues and eigenvectors. And it turns out that the eigenvalues, I like to order them in decreasing magnitude. And I would like to only retain the biggest K eigenvalues. And for each of the biggest K eigenvalues, I take the corresponding eigenvectors for those K biggest eigenvalues. And those are called my principal components. Yeah,
How do you decide like how much you want?
we'll talk about that. Yeah, that's a very good question though. How do I decide what K should be? How do I know how many eigenvectors to take? And that's a very interesting question, and there are some answers to it. But yeah, so once I have my eigenvectors of my principal components, I just multiply each data point by the corresponding eigenvector. And then I have my data is now transformed into the principal component space, which is what I want. Any questions on that? Yeah.
Wait, so your PCA vectors should be orthogonal to each other?
Absolutely, yeah.
So, and your eigenvectors are also orthogonal?
Absolutely, yes.
Wait, then that implies that the matrix has to be that.
It does not.
Or sorry, it has to be it has to be
Symmetrical.
Symmetric.
Yeah, symmetric.
X transpose X is the symmetric matrix, always.
Or, yeah.
Going back to the complex value thing, because we're dealing with X transpose X in
It's,
in
It's
PCA,
a-
it's all the eigenvalues are real all the time.
yeah, so X transpose X is symmetric, and so it has all real eigenvalues and eigenvectors. So we solved that question. Thanks, James. Math is cool. So yeah, X transpose X is symmetric, and so are the eigenvectors are orthogonal, which means our principal component axes are orthogonal to one another. Any other questions on the algorithm? So if you've seen or if you heard about a singular value decomposition, I can also derive this algorithm using the singular value decomposition. They're very, very similar. I didn't want to talk about SVDs today because I assume that most of you haven't heard about them, so I didn't want to confuse you all. But if you've heard about an SVD, SVD and PCA are very intimately related. So here's another derivation, another way to look at PCA. So this is kind of a messy formula, but don't worry about it. Basically, and when I'm doing PCA, I'm trying to find a direction W that let's just say maximizes, not minimizes. So that minimizes should say that maximizes variation of the projected data. So typo, sorry. I think I'll just change that right now so I don't drive my. Oh, you changed it? Thanks. Okay. So find the direction W that maximizes, not minimizes, the variance of the projected data. So when we project the data down onto our lower dimensional space, we don't want it to be all bunched up. We want it to be as spread out as possible. We want to retain as much of the variance in the data as possible. So on this picture, if you see those blue points, I want those blue points to be as spread out as possible. And if you like math, you can look at this formula and say that I'm looking at the variance. I'm trying to maximize that variance, and that equals this, which equals that, which equals this. And you might recognize this as a Rayleigh quotient. And if you know anything about Rayleigh quotients, you know that the maximum eigenvector, the maximum eigenvector of x transpose x will maximize this expression, which confirms our previous beliefs that that the maximum eigenvalue, its corresponding eigenvector, will be our best low-dimensional representation. And so this will give us one direction, one principal component. If we want to find a second principal component, we do this again. And it turns out that the new direction, W2, is the eigenvector corresponding to the second biggest eigenvalue. And if I want 100 principal components, I do this 100 times, and I use my top biggest 100 eigenvectors.
Wait, what do you call biggest?
So when I say biggest, I mean the eigenvectors corresponding to the biggest eigenvalues.
Oh, okay.
Yeah. So remember how the first step, after I can compute the eigenvalues of x transpose x, I want to order them in decreasing magnitude, and then I only retain the biggest k eigenvectors corresponding to the biggest k eigenvalues. That's what I mean by biggest. So how do we choose k, the dimension of the subspace? So as a heuristic, if I were to plot the number of eigenvectors, also called principal components, on my x-axis and the percentage of variance captured, then a curve would look like this. And you see that as I retain more and more eigenvectors, as I have more and more principal components, I'm getting closer and closer to capturing all the variance in the full data set, in the high dimensional space. So as a heuristic, I can look at the inflection point of this graph and say, oh, okay, it looks like 5 is a pretty good number to keep. More sophisticated and more widely used, and what I recommend you do, is to use cross-validation to choose k. So choose a bunch of different k's, run your PCA, do some kind of analysis with it, and see what gives you the best results or accuracy, depending on what you're doing. And then this thing in the top left corner, r sub k, is basically what I have on the y-axis here. It's the proportion of variance explained. So on the top left, I have the sum of lambda I squared from 1 to k. I'm sorry, those are the k biggest singular values. And I divide that by the sum of all the singular values. And that's the proportion of variance explained. Any questions on that? And we'll see, when we see our demo later, we'll see how choosing this number affects our results. So sometimes, even though you have more variance explained with 15 principal components, your results might be worse than choosing 5 principal components, even though when I choose 5, I don't have all the variance captured. And that might be because, going back to what we talked about originally, we might have redundant features, or we might have some noise in our data that we can kind of extract by choosing less principal components. So we don't always want to maximize the y-axis here. Sometimes we can get away with getting 80% variance captured, and we might have better results there. Yeah?
Can we use this technique to, like, if you have some, I don't know, something like sound that's like really bad audio or something, and you can like extract the major components of it or something?
I think you can.
Use it to get,
Like signal processing stuff.
yeah, for signal processing.
Yeah.
Just also as like an interesting side note, sometimes you can use PCA, but rather than taking like the biggest principal components, you take the smallest principal components, and in some applications it's actually better to do that. For example, things like anomaly detection, where you're trying to detect things that are different from like a certain class. It turns out that you can often do way better just choosing the ones that explain the least variance as opposed to the ones that explain the most variance.
So again, as a first step, looking at the variance captured is a good first step to choosing k, but it's not always best to choose the biggest k for a lot of reasons. As I increase k, I increase my computational complexity, and sometimes will increase the noise that I have. So sometimes choosing a smaller principal component number is better. So that was about PCA, and now I wanted to talk to you a little bit about nonlinear dimensionality reduction. Again, PCA was a linear dimensionality reduction technique. So here's the difference. In linear dimensionality reduction, we have that the components of the low dimensional approximation are given by a linear combination of the components of the high dimensional point. So I look at my high dimensional point and I approximate it with a linear combination of the principal components. Sometimes data is expressed in a low dimensional surface embedded non-linearly in a high dimensional space called a manifold. So if you look at this picture, I have this data embedded non-linearly, and it turns out that this requires, to get it down to this form, I need to do some kind of nonlinear dimensionality reduction. Running a PCA on this would give me nothing very useful. So again, the goal is to recover a low dimensional surface, low dimensional approximation to this weirdly shaped nonlinear surface. Again, the problem with PCA, linear projection methods, is that they can't capture intrinsic nonlinearities. We want nonlinear projections. So a couple ways we can do this. There's a long list of nonlinear dimensionality techniques, dimensionality reduction techniques, but two that I mentioned here are, because we just talked about PCA, you can do another version of PCA called kernel PCA, where this sounds kind of counterintuitive, but before we reduce our dimension, we transform our data into a higher dimension, and then we perform PCA. So we have our data, we raise it up, and then we lower it. And that works well in practice. Don't have time to talk about details for that today, but something that I did want to talk about more are autoencoders, which are very, very interesting. And then, like I said, there's many more that we can touch on, but don't have time. So let's talk about autoencoders. So coming back from our previous few weeks on neural networks, we see them again. Pretty cool stuff. So an autoencoder is simply a feed-forward neural network, which is trained to approximate an identity function. So I have a vector as my input, and I have the same vector as my output. And in the feed-forward step, I have a much smaller number of hidden units. And then I want to, for my output, I want to expand the small number of hidden units back to my original dimension of the vector. So that's the idea behind an autoencoder. And as I train this neural network, it knows how to better embed this high-dimensional vector into this low-dimensional hidden layer. So that's the training process here. Is I'm trying to get a better and better approximation in the hidden layer to my full data vector. So that's an autoencoder. Useful in natural language processing, which I'll touch on next. So here's how we can use autoencoders in natural language processing. So when I tell a computer a word, I usually tell it in the form of a one-hot vector, which is a vector with a 1 in one element of the vector and zeros everywhere else. A problem with this is that these one-hot vectors can be very, very high-dimensional, which is a big problem we just talked about, high dimensionality. And in parentheses, I say there are 13 million words in the English language. So, I mean, if I have all the words, I can have a 13 million dimensional vector. Doesn't sound very fun to compete with. So a goal here is to represent the words in terms of their most common neighbors. So if I do some kind of embedding of these words, I can reduce them to a much smaller dimensional space. And hopefully once my word embeddings are very highly trained, I can see them, look at them in a much lower dimensional space, and I can see that words with similar meanings are much closely clustered together than words with dissimilar meanings. So here I have, in the red dots here, I have the words paint, color, and finish. I would expect them to be pretty close to one another. In the light blue, I have kitchen, table, toilet, faucet, bathtub, sink, and vanity. In the top, I have the yellow circles. I have refrigerator, oven, microwave, GE, LG. So companies and appliances are, even though they're kind of very different topics as we think about them, it makes sense that I would have GE and LG next to all these kitchen appliances because those companies make those appliances. And so this is what you get when you have very highly trained word embeddings. You can cluster, or you can look at words in a much lower dimensional space rather than having that 13 million dimensional one-hot vector. Yeah?
What happens if a word has different meanings? Like say finish has like several different means and the context. Like, is it possible to have multiple vectors appear, or vectors appear multiple times? In this kind
That's a tricky question. Natural language processing is very difficult.
okay.
This is a problem that is often faced. So another example is the word pen. If I have a pen, I can talk about a writing utensil, or I can talk about a cage.
Yeah.
So this is a problem that's hard for computers to
But-
understand. James has a good answer for this, though.
But like you won't end up with multiple vectors for the same word. You'll only ever have one vector for the same word. Whether or not that represents both meanings, that's a question to be asked. But it will. Each word maps directly to one vector.
Oh, so it's not like there's 13 million words, so you have a 13 million dimensional vector. Say there's like 14 million meanings, then you'd have a 14 million dimensional vector?
No. So each.
Chime in with one other answer. So like if the word's only represented by one vector, you're not going to have multiple vector encodings for this one word. But sometimes when you're training your model, you don't just consider the features of that word. Maybe it's for natural language processing, an RNN or something where you're considering other words in the sentence, other words nearby. All of that, when incorporated with that word, can give you which meaning it is.
Oh,
Does that make sense? So the other features you add in can like give you which meaning it is.
So the vector that actually represents the word is the like values of these neurons in the middle layer. So like your vector is not like 14 million dimensional. It's a smaller dimension. You might have many of these vectors, but the dimensionality of your vector is this dimension.
okay.
If that answers your question.
Good question.
Yeah. So when you do this autoencoder process on words, for example, what information do you give it such that it can actually embed them in a way that represents meaning?
There's different answers to that. You can look at the context of the word, or you can try and predict the word from its context. There's different ways to do that.
The main way, I guess the most common thing people use is something called word2vec, and if you're interested in that, I'd look up the paper on word2vec.
Is this you now?
Yeah, I think so. Yeah. Before I do this zebrafish example, this picture made me think of something really cool that Google did. So this is like 10, I don't know if I can get this full screen.
It's good enough.
Okay. Yeah, so this is like 10,000 words that are first used this autoencoder method, or actually technically word2vec, but it's based on autoencoders, to make them into a vector, and then we use PCA on it so that we can visualize it in just 3 dimensions. And so you can see here, you can like look up words on the side here, like Python, and then you see Java. So the ones that show up in yellow are the ones that are closest to that word in the original vector space. And then you can see where they lie in this PCA, in the principal component space. So you see Python, some of it's Java, some of it's like other animals and stuff like that.
Does anyone have an idea as to why nonlinear dimensionality reduction works much better for words than linear dimensionality reduction?
Construct sentences linearly.
Yeah, language is a very nonlinear thing. Exactly.
This is just another cool example of PCA, but we can actually do PCA on images. So if we look at the MNIST image data set, and here they visualize it really nicely, you can sort of see the actually what the images were and where they fall in this space. So you can see 9s are grouped with 4s, and like 1s have their own little section, and 0s and stuff like this. And just as an example of another type of nonlinear dimensionality reduction, there's something called TSNE, T-distributed stochastic neighborhood something. But basically it's a nonlinear method of dimensionality reduction that works incredibly well for some things. Like for MNIST, I think this is going to turn out really well. I haven't tried it on here, but for some things, it's basically a stochastic gradient descent way of doing dimensionality reduction based on like estimating similarities between things as probabilities. It's really cool. But basically you can see it actually moves because it's doing gradient descent. So it's going to like, it'll take a while to get to something nice, but it will get to something pretty nice eventually. Yeah, so we can come back to that.
Let it train for a
Yeah.
while.
Yeah. But the main application I was going to talk about is application of PCA to exploratory analysis of zebrafish brains. So zebrafish are these super cool fish that they discovered have a certain gene that if you deactivate it, they actually don't produce melanin, so you can see through their skin. And then there was another gene that they found that could force them to have their neurons light up especially bright when they're activated. So you can actually take these images of these zebrafish and see their brain activity through these images. So so this colored image is not exactly what you see in the when the zebrafish is actually, that's based on the PCA, but I'll show you. Yeah, so you get these images sort of like this of their brain activity. So here they have a lot. Their brain is actually spread out across their whole body. They have neurons almost everywhere. So you get these bright neighborhoods. And basically what they did is they exposed them to repeated stimuli and see how their brain changes through these stimuli. And then they took that, how do I zoom out?
It's not working.
Okay, well, rip. Okay, well, anyway, basically they took these images and converted them into time series by taking the mean luminosity across the whole image and see how that changes over time. So in the upper left here, it's pretty small, but you can see each of these little points are a data point from their experiment, and you can see the time series from that. And then they took these time series and took samplings from the time series. So at X number of seconds, they would take a sampling and turn that into a vector. And then they took that vector and ran PCA on it to get this sort of two-dimensional clustering over here. And then they also did the same thing, rather than in the time dimension, in the spatial dimension. So they took the average of these luminosities across time to get this sort of spatial map. And then they took PCA across the spatial dimension, and each of these colors represents one of the principal components in the spatial domain. So you can see sort of the principal components of their brain activity in these sort of different areas, and it's very clustered. They have principal components that are symmetric up here and here and here, and then this sort of blue region through the middle. I thought it's pretty cool, especially a cool application of PCA. I don't know exactly what their paper concluded, but I thought it was a cool example of the use of PCA. So going through this Jupyter notebook of theirs, you can see that they take for example, this is an image where they took the mean. Actually, I think this is the mean image across all their experiments, I'm pretty sure. And so they took the mean across time and the mean across all their data points. And then they do the mean across time of a single data point, and you can see that, and then turning into the time series like I talked about, and then sampling from that time series, and then doing this trial-triggered averaging thing. Because they did these repeated stimulus experiments, they wanted to turn it into just one stimulus as a data point rather than the repeated stimuli. And then they took PCA, and you can see these principal components in the time dimension, and then in the spatial dimension. Yeah. So yeah, lots of pretty pictures. It's pretty cool. And this is the same plot, pretty much, that you saw on their website. And I think they're doing some, I'm not sure what they're doing for that last plot, but yeah. Yeah, so that was what I had to say about that zebrafish example. But I think it's a pretty cool application of how PCA could be used for things that you wouldn't expect. Especially in biology, PCA is used more often than you'd expect.
Especially in biology, that's where we have very high dimensional data.
Oh, maybe we could look at this. It's still going.
How's it going? Still descending?
Yeah, it takes a long time, but
Cool. So as you're well aware, there are tons of applications. One kind of canonical application of PCA is in Eigenfaces. So it's where we talk about recognizing faces. So let me Back to present. So face recognition with eigenfaces. So now I'm supposing my design matrix has n images with d pixels each. And face recognition is the following problem. Given a query face, compare it to all the training faces and find the nearest neighbor in d-dimensional space. So if I have a dictionary and I have every face of all the Americans, of all Americans in my somewhere saved, and I have a new picture, maybe I have a criminal who's robbing a bank and I have a camera and the camera scans his face, I want to see if this guy is a wanted criminal or something like that. So I have a query face, this image of this person at the ATM, and I want to see if he is one of the criminals that I have in my database. So problem with this is each query can take order nd times. If n is very large and d is very large, this can take a lot of time. So an idea here is to run PCA on faces and reduce to a much smaller dimensional space. Maybe my new dimension is called d prime. Now when I reduce my dimension, each query now only takes order nd prime times, when hopefully nd prime is much smaller than nd. So here's what an eigenface is. So an eigenface is just a fancy name for the principal component of when I'm looking at faces. When I have face data, the principal component of each face, the principal component of the faces of the face data is also called an eigenface. So each image would have d eigenfaces, and I only want to keep a certain amount of them. I only want to keep d prime eigenfaces. So maybe if this is my original image on the left, if I look at this is very blurry, I'm sorry, but that should say k equals 4. And if that's my fourth eigenface. That's the eigenface. That's the fourth eigenvector, corresponding to the fourth biggest eigenvalue. And this is my 50th eigenspace. So you see it's much blurrier. There's less information contained in the 50th eigenface as compared to the fourth eigenface. That's what I would expect. I expect that as k is smaller, the faces look more and more realistic. I'm explaining more and more variance. And as k gets larger, each subsequent eigenface is explaining less and less variance. So that's why this one is pretty blurry, and the k equals 4 eigenface is not as blurred. So let's do a demo on this. Okay, so I imported some stuff. Let's load the data. So what do I have in my data? In my data set, I have 1,200. That's really small, sorry. In my data set, I have 1,288 images. Each image has 18,050 pixels, very high dimensional. And I have 7 classes. So I have 7 people in this data set. I have celebrities here. I think I have George Bush, Donald Rumsfeld, a bunch of people like that. I forgot who, but we'll see who exactly they are later. So again, recap, I have 7 different people. I have a bunch of images of their faces, in particular 1,288, and each image is, I believe, 35 by 50. 37 by 50. Each image is 37 by 50. So I want to reduce the dimension from 1850 to a much smaller dimensional space. So I run a PCA. So let's say I retain 900 principal components. So you see that I explain 99.99945% of the variance. So just by cutting the dimension in half, I still retain almost 100% of the variance. Now if I change this to 100 principal, or let's do a really extreme example, let's take it down to 10 principal components, I still get 63.6% of the variance. And this is reduced from 1850 to 10. That's a very significant reduction. I don't really like 63.6, that's not very much variance, so let's make it a little bit higher. Let's try 100. So with 100, I explain 92.6% of the variance. Okay, pretty happy with that. Let's try 200, 97.17%, and you guys can play with this on your own. This is posted on the repo. But for our first try, let's try 150 components and see what happens. So with 150 eigenfaces, I still retain 95.5% of the variance. Okay, so let's visualize the eigenfaces. So this is just a helper function to help visualize them in a nice format, and then I can plot a gallery. So these are the top 35 eigenfaces. So each eigenface is a principal component of each image. So what do you guys think of the eigenfaces?
Very.
I think it's weird.
Yeah.
11 definitely looks like Donald
What happened to 14?
14 has some trouble. I'm not sure what happened to 14.
11 is a dead sync.
Yeah.
14 looks like Slenderman.
Yeah. So it's pretty crazy, right? That I can. It's pretty crazy to me that I can only retain 10 of these eigenfaces, so the top 10, and I still can explain most of the variance in my face data. So those are eigenfaces, visualized. Okay. So now I know we've been talking about unsupervised learning, but let's say I want to do some face recognition. So here I want to recognize, given a query face, which one of my 7 celebrities is it? And so we haven't talked about this specific model this semester, but I'm going to talk about something called, or not talk about it, just implement something called an SVM, support vector machine. Don't worry about what it is, what it does. If you've seen it before, great. If not, it's just another supervised learning algorithm. I like it. Works well. So this is actually for your projects. You might want to do something like this, where you do a CV grid search. So here, in an SVM, I have a lot of different hyperparameters. I have the kernel, I have C value, I have gamma, I have a lot of different hyperparameters. And so to find the best combination of hyperparameters, I can do a grid search, and that'll find which model is best. So if I try a grid search on this data, on the PCA data, then it'll be done in a few seconds, and it'll tell me which model is the best that I should use for face recognition. Maybe about 10 more seconds. Great. So there's my best model. It's a SVM with C equals 1,000, a RBF kernel, a radial basis function kernel, gamma equals 0.05, polynomial degree 3, and that's the best model for me here. So that kind of took a while. So what if I change the number of components to 20? How do you think that'll be a lot faster to do? It should be a lot faster. Not as fast as I wanted.
Yeah, I don't think you ran through the other stuff.
I didn't have to run for the others. That was just plotting. But that was still a lot faster, right? But for the purpose of accuracy, let's go back to maybe 100 and see what happens. Still should be decently fast. Now you can imagine that if I took all 1850 pixels and I tried to fit an SVM, that would take a lot longer, right? So a big benefit of this is to speed up computation. Yeah.
Does this also reduce overfitting using PCA?
Yeah, I can. So we'll look at the accuracies in a second. Okay, so this is my best model. Let's run it. And so I ran my model, and I have an overall 86% accuracy. So for Ariel Sharon, I was able to correctly classify 100% of the faces. For George Bush, I only got 86%. For Hugo Chavez, I got 100% accuracy. Donald Rumsfeld, 89%, etc. So here's a confusion matrix. And yeah, so that's with 100 principal components. What happens if I go to 10? How would this accuracy change? Let's see. I expect it to go down. Well, how much further is it going to go down? How far is it going to go down? Hurry up. Should not take this long. Okay, here we go. So my accuracy, when I only took 10 principal components, my accuracy was 43%. So not as good. So I want to find the best number of dimensions to keep. So to do that, I can do some kind of cross-validation. That's going to take way too long to do in a demo. But as an example to show you that taking a higher number of principal components isn't always better. So remember before when I had 150 principal components, I had 86% accuracy. Let's say I take 500 principal components. So now I'm explaining a lot more variance. So with 500 principal components, I'm explaining 99.7% of the variance, whereas with 150, I only had about 92%. So now I have a lot more variance explained with 500 principal components, but let's see what happens to our accuracy. Again, just wait a little bit.
Can you go back to the projector?
This?
The other thing.
Oh yeah, sure. See how it's going.
Is it still going?
It's still going.
Is it still going?
No, this. I'm pretty sure Google will give you about 0 computational power to work on this. So like they slow it down a lot because like you can imagine if everybody tried to do this.
But it's looking pretty good though.
Yeah, can
But,
you pan around it?
There's actually a picture that shows really well. I found. It's already much better than PCA, but
Yeah, they're like all perfectly grouped together right now.
Yeah.
Here, if you.
At least the ones are.
Oh, also that TensorFlow projector thing has a feature where you can put in your own data and labels, and then it'll run PCA or TSNE or whatever you want on it. So it's pretty cool. You can, and then like you can search through your labels and stuff. It's really useful. So if we scroll down here, so this is PCA. This is 2 dimensions instead of 3, but you can see that it's not great.
So think about what we're doing though. Each MNIST image has 784 pixels, and we reduced it to 2 dimensions. And this is how it looks in 2 dimensions. So not that great.
But if you scroll down to TSNE, this is TSNE in just 2 dimensions. You can see it's pretty much perfectly clustered.
So TSNE again, nonlinear dimensionality reduction often does a lot better than linear dimensionality
I
reduction.
think this plot was trained for many hours though. But
Yeah. Okay, so this should be done training my model. And so look, my accuracy went down. Before I took 150 principal components and I had 86% accuracy. Now I took 500 principal components, so I explained a lot more variance of the data, but my accuracy went down 8%, pretty significant amount. So again, the kind of a way to cross-validate is to try different amounts, different k's, and find which k gives me the highest accuracy. So maybe we can think of having 500 principal components as overfitting. So again, the point I really want to stress is that when we do PCA, when we reduce the dimension, not only do we sometimes improve accuracy by getting rid of noise, but we also greatly improve computational speed. So it's like a win-win. Improve accuracy and reduce computational complexity. So let's visualize some of these predictions. Let's see how my model did. So here's a picture of Rumsfeld on the top left, and it predicted Bush. Second image was it predicted Bush, and the true image was Bush. We did pretty good with Bushes. Yeah, I mean 78% isn't too bad. A lot of Bushes here. Yeah. So this one is Bush, but my recognition algorithm thought this was Powell, and yeah. So maybe I'll go back to 100 principal components. So look, I reduced the principal components by 400, and I'm only explaining 92.7% of the variance, but I bet you my accuracy will go up.
What would be a situation where you wouldn't want to use PCA? Like, what would be worse? I guess that would be.
I don't know.
That situation I was talking about with like anomaly detection, like if you were just to use basic PCA and take the top X components, you wouldn't do very well. Which has to do with like variance not being correlated to like anomalies. So if you imagine you're trying to detect like this 1 in a million thing, like you don't really care about the variance so much.
So I reduced my principal components to 100 from 500. Now I'm only looking at 100 principal components, but my accuracy went up 8%. So pretty good. And maybe I think this is because there's some noise in my data, and principal components analysis helps me segregate the relevant information in the images from the noisy stuff. And so let's visualize some of my predictions again. Okay. So pretty funny. Here's Chavez right here, pretty upset. Cool. Any questions about anything? Any questions? Either you guys have no idea what I'm talking about or you understand it perfectly. Yeah. X transpose X. So X transpose X is always a symmetric matrix. It's always positive semi-definite. Those are just important things about X transpose X to know. What's that form called? X transpose X? There's a name for that form.
What's the
Quadratic form. Thank you. Yeah.
Also symmetric.
But it's the quadratic form of X. X transpose X. Or no, it's yeah.
How expensive is it to find eigenvectors and stuff?
The computational complexity of eigensolvers are, I think it's like n squared d, something like that. Here.
Well, okay.
But if you have like the million features, it's gonna blow up on you.
Yeah.
Yeah, it's about on the order of n cubed.
Oh man.
So again, but luckily, when we do this kind of dimensionality reduction, we don't have to compute all the eigenvectors / eigenvalues. Before we extract the k biggest ones, we can only compute the k biggest ones using some truncated SVD solvers or a lot of advanced linear algebra solvers. We don't have to compute the whole set of eigenvectors, which saves us a big amount of cost.
So you can just like compute like the k amount that you want of the eigenvalues, or like you compute all the eigenvalues, figure out the largest ones, and then compute the eigenvectors of those.
Or you can just compute the k biggest eigenvalues.
Yeah. So you first, but wouldn't you have to first know like all the eigenvalues before you know the k biggest ones?
I think you could do like a truncated SVD to avoid that.
Oh.
So, just as a review of what's all been taught so far, eigenvectors are basically tell you what's important about your data set. So you use
Eigenvectors give you the direction that preserves maximum variance in your data. So
okay.
I guess, yes, importance.
Okay. And then your SVDs are your eigenvectors.
For fun, I'll show you what an SVD is. So every matrix A, so let's have a matrix A, symmetric, non-symmetric, any matrix positive or not positive can be decomposed into the following decomposition of product of three matrices: U, sigma, V transpose. And this is what an SVD is. U is the matrix of left singular vectors, V is the matrix of right singular vectors, and sigma is the matrix of singular values. It turns out that if I take, I multiply U times sigma and take the ith row, that's the same thing as what I said here. So here I compute the coordinates x times vi. X times vi is my transform coordinate in my principal component space. It turns out that the ith row of U sigma is the exact same thing of my data transformed into the principal component space. Of the ith data point transformed into the principal component space. So that's what I meant by PCA and SVD being intimately related. But again, I didn't want to go into that much because this is, a lot of you probably haven't seen that before. But yeah, that's all we had for you today. I hope it was interesting. We'll stick around if you have any question about the projects. But yeah, that's it. Thanks.